Hey everybody. So today we're going to be doing a tutorial on correlations in the different programs. So correlation is simply the strength of the association between two different variables. So we're going to be doing this in Excel, JASP, SPSS, and R. So we'll get through them pretty quickly. They're pretty easy to calculate in all four of these programs. So we're going to start off in Excel. And realistically, the easiest way to do it in Excel, to do a correlation, is by using the correl function. We've seen this before. It's equals, C-O-R-R-E-L, correl, and then you have to just select the two columns of data that you want. So height, comma, shoe size. Close brackets. And we see we get a value of 0.8986. So we know that correlation values range from -1, which means as one variable is increasing, the other one's decreasing, to +1, which means while one variable is increasing, the other's increasing at the same rate. So a correlation coefficient of 0.9 basically means that there's a strong relationship between them. And what we can do is interpret this by squaring this value. And that really will give us an idea of how much of the variance in the two variables is shared. So if we take this value and square it, which is very easy, equals this value to the power of 2, what I get is a value of 0.8076, which basically means that just about 81% of the variance is shared between these two variables. Our next question is this a significant correlation? And in order to find out that, we can do two different things. First, we could go to our R table, and I've put that into the Excel workbook for you here as a separate tab. So if I click on that, we're going to need two pieces of information. First of all, it's going to be our p-value that we want to see what we need to exceed as a critical value. And second is our degrees of freedom. And for correlations, our degrees of freedom is the number of pairs minus 2. So in this case, we see that we've got 22 pairs of data. So we've got 22 subjects here, minus 2. So our degrees of freedom is going to be 20. So if I go to the R table, we go down to degrees of freedom of 20, and we see that in order to have a p-value of less than 0.05, I needed a correlation coefficient of 0.423. We can even look farther over, and we see that for less than 0.001, I need a correlation coefficient of 0.652. But we know that ours is 0.89, so it is quite high. The other way we can do this is we can take our correlation coefficient, and I'm going to copy it, and I'm going to go to Google and search for R to p-value. So if I do that, I get this top hit here is quick p-value from R score calculator. So if I click on that, it asks me to input an R score. If I put that in, that's 0.8986, and asks for my N, not my degrees of freedom here, my N, which was 22. And I calculate, and it shows me my p-value is actually less than 0.00001. So that's clearly significant. Okay, so the next thing I want to show you is that we can correlate height with sex as well if we want. And this is a special case of the correlation coefficient. It's called a biserial correlation, and that's when one of the variables is continuous and the other one is categorical with only two categories. So in this case, we're going to run a correlation. So let's use the same function, equals correl, height, comma, and I'm going to put 6 here. Need to use a numeric. It's not going to work with these M's and F's. And we see we get a correlation coefficient of 0.7575. And again, we know that that's going to be significant because our degrees of freedom is the same as what we saw before. We can actually take this and calculate the exact p-value by going back to our calculator here, putting this back in, 0.7575, calculate, and I get a p-value of 0.000045. Now, what's interesting about this is I want to show you that, in fact, if I run a t-test, so let's say this was p-value was 0.000045. But if I run a t-test on height as a function of sex, so I'm going to run a t-test between the heights of the females, comma, heights of the males, comma, two-tail, comma, type, it's going to be an independent t-test. What we see is we get the same number, 0.000045, or 4.5 times 10 to the negative 5. What that means is that this correlation and the significance value is exactly the same thing as doing a t-test when you're doing a biserial correlation. Okay, so let's move on to doing a correlation in SPSS. So I'm going to pull up SPSS with the same data, and the data file is called correlation.sav. Okay, so here we are in SPSS, and we've got the same data, and what we're going to do is run a correlation analysis between height and shoe. So it's really easy. We just go up to Analyze, scroll down to Correlate, and click on Bivariate, because we're going to run a correlation analysis between two variables. So in bivariate correlation, we're going to select height and shoe and put them in as variables. We're going to select the Pearson correlation coefficient. We'd use these other ones in cases where we don't have parametric data. I'm going to click on Options, and I'm happy with what I've got here. So I'm just going to run the correlation analysis. And what we see here is we get something very similar to what we had in Excel. So we have part Pearson correlation is 0.899 and significance value is less than 0.001. Okay, so that was pretty easy. Now, the other thing we can do is we can also run a bootstrapped analysis, which will give us 95% confidence intervals around our correlation coefficient. So let's do that. So if I click on Analyze, Correlate, Bivariate, and this time I'm going to click on Bootstrap, click on Perform Bootstrapping, and I want to select Bias Corrected Accelerated. Typically, this is a better choice than percentile for most of our analyses. And click on Continue and OK. So we'll see it's going to take a little bit longer to run that. And we see I get the same correlation table, same correlation value, but this time it's given me 95% confidence intervals around my correlation coefficient. And what we can see is that even at the lower bound, it's still a very strong correlation coefficient, and I can be very confident in the strength of my association between my variables. Okay, so why don't we go ahead and have a look at correlation between not only height and shoe, but height and shoe and sex. So we're going to add that into our correlation and make a correlation matrix. So if I go up to Analyze, Correlate, Bivariate, and now I'm just going to add sex in as a variable here. And I'm going to leave all my other options the way they are. Click OK. It's taking a little bit of time. Now we see I've got various different correlation coefficients. One between height and shoe, which was the same as we saw before, and height and sex. I get another correlation coefficient, 0.758, and the significance value, again, is less than 0.001. And we have our bootstrapped confidence intervals for our Pearson coefficients. We also see that we have shoe correlated with height, again, and shoe correlated with sex, and those variables are just repeated down here. Okay, so what's interesting is I see that these are a little bit different. So what I'm going to do is I'm going to graph my data and see sort of what the slope of the correlation looks like. One easy way to do that is by using the Graphs tab. And I'm going to go down, and just to make my life easy, I want to click on Legacy Dialogues. We see we have a few different possibilities here. The one that I want for this analysis is scatter and dot. I'm going to click on just a simple scatter and click on define. Now it asks me, what do I want? I've put in y-axis, height, x-axis, shoe, and I'm going to set markers by sex. Now, if I click on OK, it'll draw me a simple graph of my data. And what we see is I've got sex 1, that's my female data, and we see they've got the smaller heights and smaller shoe sizes, and the male data has the larger heights and larger shoe sizes. Now, one thing I can do if I'm a little concerned about this data is I can run what's called a partial correlation. And so the partial correlation is going to control for that third factor. So I can run a correlation between height and shoe, but controlling for any effect that sex might have on these data that we can see here. So the way to do that is go to Analyze, Correlate, Partial. And in the Partial Correlations dialog box, I'm going to select height and shoe size as my variables. And in controlling for, I want to put sex in. Now, I'm going to just run that the way it is right now. So Options, Continue, Bootstrap, no bootstrapping for now. I just want to run that and see what I get. And what we see is I get a partial correlation coefficient here where height is correlated with shoe size 0.803. Now that's a little bit different than what we saw when we included everybody in the analysis. So what I can do is rerun that analysis just to see how much it's changed. So if I go back down to Correlate, Partial, and I select Options, Zero Order Correlations, hit Continue, and OK, what we can see is the first set up here where the control variable is none, I get my first set of correlations, which is what I had before. So my variable for height with shoe size goes down from 899 to 0.803 when we control for sex. Okay, so let's move on to JASP and run these analyses in JASP now. So when I open up JASP, we see I have the same data file again. Now, again, JASP is very easy to run correlations. The way you're going to find it is under the regression menu tab item. So I'm going to click on that and just click on correlation. And when I do that, we see something very similar to what we saw in SPSS. So I'm going to select height and shoe size as my variables. And what we see is I get my Pearson's R and my p-value. I can then condition on sex, and we get that same 0.803. So it's very easy to run these correlations. The other thing I can do, which is very easy, is to plot these data using a scatter plot if I want. And we see here we get our height and shoe size graph very easily. All right. So now let's move on to R and do a correlation analysis in R. Okay, what we see here is we've got our previous script file here and our old data frames in here so far. So we're just going to keep adding on to this file. So the first thing we're going to do is import our correlation data set. So I'm going to find that and import the correlation.csv. Okay, and I'll just leave it named correlation, and I'm going to select that it's got headers, yes, and I'm going to import. Okay, excellent. Now, if I go back to week 1, what I'm going to do is just select just my base here that I'm going to use to create a new set of commands. So into a data frame that I'm going to be my working data frame, I'm going to put correlation. And in R, it's fairly easy to run correlation. So the way we do that is by using the function cor. And I'm going to correlate, in this case, if we look at correlation, I need height underscore inches and shoe underscore size. So height underscore inches, comma, shoe underscore size. Now, if I run that command, what we see is I get one little command out there. We get a correlation coefficient of 0.898, which is what we've seen in all the other programs. It's actually 8.899 because it's 8986. Okay, so the next thing we can do is we can add a little bit more information into this. So we can use the core.test function with the same two variables. In fact, I could have just copied this, paste it there. I'm going to add core.test and run this. And what we see is not only do I get the correlation coefficient, but then it gives me an entire set of information. So I get a t ratio, degrees of freedom, a p-value, 1.34 times 10 to the negative 8, and we have 95% confidence intervals for my correlation coefficient, which is 0.8986. Okay, excellent. So one thing I might want to do that I've done in the other programs is plot my data. Very easy to do. I can just use a plot command. I'm going to plot height in inches by shoe size. Like this, I've got one extra bracket there. Let's get rid of that. And I'm going to run this. And you'll see up behind me pops my graph of all of my data as height as a function of shoe size, or in this case, it's actually shoe size as a function of height. Okay, so next step, do we want to run a partial correlation? So I'm going to select my core.test, copy and paste it. Again, I just use Control-C and Control-V. On Mac, it'll be Command-C, Command-V. And instead of core.test, it's going to be pcore.test. And then I need a third variable. It's going to be height, shoe size, and the last variable is going to be sex. But in fact, it's actually called sex1 is numeric. I could use sex1 or sex2 here, but I'm going to use sex1. And now I'm going to run this. And what we see is we get my correlation coefficient, but now my partial correlation coefficient gives me that value that we saw previously in the other programs, 0.80250, and I have my p-value there as well, 1.2 times 10 to the negative 5. So the last thing, if we want, a lot of the time we're going to take these models that we create and create new objects for them. So instead of just going pcore test and running that each time, I can actually save it as, let's just call it pcore model. And I'm going to put that test into the model. So when I run this, it does all of these things. And now I've got this new pcore.model. And if I want to see what's in that model, it's very easy. I just type pcore.model. If I just ran that command, again, just to run that one command, I just need to hit Control-Enter. We see it just pulls open that value. So now I only ever have to hit pcore model. I don't have to type this whole thing out again because I've saved this model into a new object. Okay, so that's all I've got in terms of correlation. The next tutorial is going to focus on regression.